Alors, rebonjour. Donc, on a maintenant la session méthodes et outils de conception. Donc, je vais laisser Kevin Martin présenter cette session.
Bonjour à tous. Donc, on va inviter John McAllister on stage, comme on dit. So we're going to switch in English for John. So it's my great pleasure to present John McAllister, who is a member of the academic staff in the School of Electronics, Electrical Engineering and Computer Science at Queen's University, Belfast. His work studies computing for signal processing and artificial intelligence, with a focus on non-von Neumann technologies, particularly neuromorphic, quantum, and programmable hardware technologies. He was chair of the IEEE Technical Committee on Design and Implementation of Signal Processing Systems in 2020, and he is founding chair of the IEEE Technical Committee on Applied Signal Processing System. He is a member of the Executive Committee of the IEEE Task Force on Rebooting Computing, senior area editor of the IEEE Transactions on Signal Processing, founding chief editor of the IEEE Signal Processing Society Resource Center, and co-founder of Analytics Engines. So thank you, John, for being with us, even on distance. So now we are all listening to your talk.
Okay, thank you very much. Can I just do a mic check first? Make sure that you guys can hear me okay, yeah?
Yes, great.
And you can see the slides that I've got at the moment, yeah?
Yes.
Yeah, okay, right, great. Thank you very much for that. Extraordinarily lengthy and detailed introduction. And thank you very much for the opportunity to present, of course, to you guys and for all of you who are listening either in the hall or on the Zoom call, for coming along to listen. It's a great pity that I'm quite sad that I can't be in Rennes, but unfortunately, my government has decided that if I wanted to go to Rennes, I would have to spend 10 days in a hotel in London when I came back. So my wife decided that wasn't a great idea. So so I had to stay here. But I'm quite sad that I'm missing the Rennes experience. So actually the nature of this talk, I'm going to talk a little bit about quantum computing. The nature of this talk, this isn't my immediate area of expertise. My immediate area of expertise has for a long time been programmable hardware and data flow computing and so on and synthesis of custom circuits and so on and so forth. But I thought it would be interesting to talk about this topic for a couple of reasons. First, because the Shivra who's coming after me is I knew he was going to be talking about spiking networks, neural networks, and I thought, well, if Shivra's going to talk about an exotic computing approach, then I guess it would make sense to talk about another exotic computing approach. But as well as that, because this work is not in any way the result of a grand plan. It's a series of happy coincidences and a punt on my part to get involved in the area of quantum computing. This is about 6 years ago now, long before it was fashionable. And some of my experiences doing that as someone who was not and is not well versed in things like quantum mechanics or quantum physics or quantum algorithms or any of that kind of thing. So I wanted to give a sort of a pure, I guess what I would call a computer engineer viewpoint on working in this area. The work that I'm talking about sort of has come to fruition last year and the front part of this year. And so hopefully this will give you an idea of the kind of difference that you can make in this area without overcoming, when you first get involved in the area of quantum computing, what appears to be fairly insurmountable barriers, technical barriers to entry. So if you believe the hype, then in 5 years' time, we're all going to be running all our programs in quantum computers. And this picture I pulled this off an IBM blog, in fact, and this is essentially IBM's roadmap for their quantum technology. So IBM are taking a fairly serious lead in offering quantum processing in the cloud and tooling to do that. And they're being quite forthright about marketing their quantum computers. And we've just, I believe, Europe has just, I believe, gained its first IBM quantum computer this year. But you can see the progression of the processors on the bottom here. So the quantum systems in the blue boxes along the bottom, you can see the progression that they expect of their processors and all of the stuff that goes around being able to use their computers. And so way back in 2019, they had the first generation quantum processor, which had 27 qubits. Nowadays, I'm not entirely sure they've actually got 127 qubits yet, but I believe that they do, if internally at least. But you can see that they're planning to ramp that up to between 1,000 and 1 million qubits by 2024, 2025, something like that. The interesting thing is that I do believe that their roadmap, at least so far in the 2 years it's been running, is more or less on track. So they're not making wildly speculative claims here just yet. And I know that a lot of the other stuff that they've talked about this year, so the Qiskit runtime, for instance, has been released. And they are developing these sorts of the other technologies. So if you believe that, then we're looking at explosive growth in the quantity of qubits that we have on a quantum processor over the next 5 years at least, to over 1 million, they hope. On the other hand, you'll all hopefully be aware as well that there is quite a bit of debate about whether this is actually all going to work. And the debate really took off in 2019 when Google published an article in Nature that talked about their Sycamore processor, which was a 53 qubit processor. And the diagram you're looking at right now, this is like a neat illustration of the structure of the processor. The first thing you notice is that the structure of this processor is extraordinarily simple. It's a regular lattice where the crosses are qubits and the blue squares or blue rectangles are adjustable couplers, which basically means connections between the qubits. And they claimed that via this 53 qubit machine, they had achieved what they call quantum supremacy, which essentially shows that they could run a program in about, I believe they said 200 seconds, that they claimed would take trillions of hours on a supercomputer. Now, there's been quite some debate about that actually since, and some people have placed severe question marks over that. But I think that whether or not, whichever side of the argument you're on, I think that there certainly is progress in this area. And I think that it's leading to extremely interesting questions. And it's leading to extremely interesting questions that computer engineers should be thinking about solving rather than the physicists or the mathematicians or the theoretical computer scientists who have dominated the area for the last number of years. So 53 qubits sounds great. And on the face of it, you would think that as the number of qubits goes up, then you can do more and more with a chip. But actually, there's a catch. There are a series of catches when you use quantum processors. So this chart is from a paper that was published just in ASPLOS this year. And it, in a nutshell, it kind of encapsulates the problem that the industry is facing right now. These are along the horizontal axis. These are all IBM processors in different locations around the world. And the group that did this work ran circuits of half the capacity of the processor. So, for instance, on the Johannesburg processor, they ran a 10 qubit circuit. In Cambridge, they ran a 14 qubit circuit. In Rochester, they ran a 26 qubit circuit. And they measured the reliability of those runs. And it was first a sort of like a standard quantum algorithm. They measured the reliability of those runs in terms of the probability that the outcome that they get is the one that they would get in simulation. And you can see the problem immediately with quantum processors in that if I'm running a 2 qubit program, then with almost complete certainty, then the result that I get is the one that I should be getting from a theoretical standpoint. But as soon as we get to 10 qubits, that's gone down by a factor of 100. Go to 14 qubits, and that's gone down by another more than a factor 10. Go to 26 qubits, and in effect, the probability that you get the correct outcome for this program is 0. The reason for this is because these processors, all quantum processors right now, are extremely noisy. They are susceptible to environmental noise. They are susceptible to noise from the qubits interfering with each other. So as you increase the number of qubits, the processor as a whole becomes less reliable. And as well as that, as you try to run longer circuits, then the processor, the reliability of the circuit, or what the fidelity is the terminology that's used in quantum communities, it also goes down. And you can see this yourself. If you go to the IBM Q in the cloud and you create a quantum program and you run it, it gives you a distribution of probabilities on the measurements. It doesn't tell you about an exact correct measurement. It gives you a distribution of probabilities. And once you go beyond a few tens of gates, you can see that that distribution of probabilities makes it very uncertain that you're getting the result you should be expecting to get. So that's a problem. As well, if you try to set this in context, if you remember a couple of slides ago, we talked about the IBM processors reaching 1 million qubits by about 2026. If you try to set in context what that means in terms of practicality, the really famous algorithms for quantum computing, and particularly we're thinking here about something like Shor's algorithm, you would need about 1,000 or to 100,000 qubits in order for that to be useful, in order for it to be able to run Shor's algorithm reliably, and Shor's algorithm is the one that has everyone very concerned about post-quantum security, for instance. Now, if I'm getting a likelihood of almost 0 for a circuit of 26 qubits, what's it going to be like if I have a circuit of 1 million qubits? And so clearly there is an issue with noise that has not yet been resolved, but potentially could be resolved. But even then, if it is, then there are other issues that if you've got a quantum processor of that scale, then the number of continuous parameters describing the state of the processor are 2 to the 1,000 or 10 to the 300. Now that's this is taken from an article by Diakonoff and IEEE Spectrum in 2018, which is a very, very good article. It's entitled "The Case Against Quantum Computing," and it's a really, really good article. What his message is essentially, a useful quantum computer needs to process a set of continuous parameters larger than the number of subatomic particles in the observable universe. So that's a lot of particles. And at least in his eyes, it rules out quantum computing being practical at the scales that are needed. Now, Diakonoff is a physicist, and I'm pretty sure that if an electronic or a computer engineer came along to talk about this, they would probably say, oh, well, 10 to the 300, of those 300, maybe 250 aren't needed, but that's still 10 to the 50, and that's still a lot of parameters. So there are significant challenges, and there is long-term doubt over whether or not this is going to take off in a meaningful way. That said, there are quite interesting things happening as well. The processors are getting to the scale where we need to think about problems that are that as computer engineers are familiar to many of us, or at least are familiar to me in my background is in programmable hardware. And I think that the major benefit, at least in the early term, is going to be in quantum classical crossover computing. So these two headlines are taken from a magazine, an online magazine called Quanta, which is not about quantum computing, but it's just about science generally, but it's rapidly becoming my favorite magazine. And this one, the major quantum computing advanced made obsolete by a teenager, is essentially a case where a teenager, an 18-year-old at the University of Texas, was studying quantum algorithms for recommender systems and figured out that they could execute essentially the same thing on a classical computer much, much more quickly than even the current recommendation systems could. So, and there are a series of those things happening that we're getting, getting hybrid like quantum classical algorithms. And I think that that's a really healthy direction for research in general. The door doesn't swing both ways. It's not, the door doesn't swing one way. It's not as if you get genned up on quantum technology, then you become suddenly an expert for all things classical. Actually, it goes both ways. I strongly believe that there is plenty of room for classical computer engineers to make a very strong contribution in the field of quantum computer engineering. And that's sort of why I wanted to give this talk, because I think that a lot of the things that I'm going to talk about are, as I said, very familiar to me, and they're very familiar problems, and the solutions are not quantum solutions. They're practical they're practical quantum engineering or classical computer engineering solutions. And so I wanted to give this because my experience has been that when I first got into this area, that, you know, as soon as you talk to anyone about this area, you're usually talking to a physicist or a mathematician, and they say something like, I've got, you know, go off and read this book, which is this thick, and it's quantum mechanics, and it's horrifically complicated, and the barriers to entry are so high, and everyone talks in all these strange terms that you don't really appreciate. You won't really appreciate what if you don't have a degree or a doctorate in theoretical physics. But that said, I think that there's a lot can be done effectively by not worrying about that stuff. So the things I heard about when I started in this area were, you know, trapped ion quantum processors and entanglement and teleportation and all this other stuff. And I think to a certain extent, a lot of that you can put at arm's length and say, well, I'll worry about that when I need to worry about it. There's a lot that we can do just by taking our skill set and applying it to quantum problems. And that's really what I wanted to bring out in this presentation. So I want to talk about a very sort of practical problem, which is transpiling quantum circuits, which is really the quantum way of saying programming a quantum computer. There's a very, I don't know, subtle problem. I don't know if you picked up on it when I had this diagram of the Sycamore processor on the slide before. And it's essentially that the, if you recall, the crosses are qubits and the blue rectangles are couplers. If I run a quantum program and I want to combine two qubits via a gate or an operation, the qubits have to be housed in physical qubits connected by a coupler. But when I run and execute the program, I don't have to have that. I don't have that constraint. That constraint is called the nearest neighbor constraint. Physically, if I want to combine two qubits via an operation, they have to be connected. But in the quantum program, which I use to define the behavior and simulation, I don't have that constraint. And so the typical design problem is you start with something on the top, which is a quantum circuit, and this is literally in the IBM Q. This is literally how you would describe a quantum program, and that program has to be transpiled onto something that will run on a processor that looks like something on the bottom. And this design entry, this is consistent design entry level of design entry for Qiskit, which is IBM's framework, Cirq, which is Google's framework. They all more or less as standard work off this approach. And as I said, I can start with a quantum circuit. So on the right-hand side, I've got here with 3 qubits, A, B, and C, and I am combining first A and B, and then I'm combining B and C via separate gates, and then third, I'm combining A and C, right? But when I put this on a quantum processor, I put qubit A in the top left corner, qubit B on the top right corner, and qubit C in the bottom right corner. So I can perform the first 2 operations because the locations of A and B are connected by a coupler 1. And I can perform the second because B and C are connected by a coupler 2. But I can't perform the third because there's no coupler between A and C. So what that means is I need to physically move at the location of either A or C, or both potentially, to allow them to be combined. Now, how you do that is you insert what's called swap operations. And so if you look, there's a double-ended line with an X on each end here. This is a swap operation, and it swaps the location of A and B. So I start off with the placement ABC going top left, top right to bottom right. But after the swap, I've swapped the locations of A and B. So B is now top left, A is top right. And because A and C are now coupled, I can perform this final gate. So when I want to transpile a circuit to a practical quantum processor, I have to go along and put in all these swap operations, right? And that's a manual job at the moment. And there isn't a tremendous amount of automation to help out with that. But most of us could hopefully think of a way to do that using just the things that we understand as classical computer engineers. And so this talk is a little bit about my experiences in trying to do that. Any automated solutions to this problem do a couple of things. The first step they do is they take the qubits and, they take the qubits and they place them, the logical qubits in the circuit, and they place them in physical qubits on the processor. Then they look at the remainder of the circuit and they figure out where to put in these swap operations. And I'm sure you won't be surprised if I tell you that that's an extremely complicated operation. So for instance, there are n factorial possible initial mappings of the circuit qubits to the processor qubits. So for our 53 qubit Sycamore processor, that means there's something like 4.27 by 10 to the 69 possible placements. Every one of those placements can result in a circuit with a different number of swaps. And remember that we want to minimize the number of swaps, because if we put in more swaps than we need, then we're taking up the space that's used by useful operations, and we're lengthening, making the length of the circuit longer, which makes it less reliable. So in Google's predecessor processor to the Sycamore, I think they estimated that for every extra gate that's added, it adds about 0.6% error to the fidelity of the operation. So we want to minimize these number of swaps. So this entire process is about minimizing number of swaps, picking the initial placement, and inserting the swaps as strategically as possible in order to minimize the number of swaps. Of course, you can't exhaustively look at all the options. So the question is, can we get to a good solution much more quickly than that? There was some work out there that looks at this, and they use heuristics, which are, again, familiar to probably all of us. Each of these arrows represents an operation. So the first arrow is placement, and the second arrow is the swap operation step. It's for, sorry, swap insertion step. And so when I want to do placement, there are approaches out there that use things like mixed integer programming or harmony search. And they work with an objective function that looks something like this. And it says, more or less, it's the cost of a placement P is you take the sum over all pairs I and j from your set of qubits, and you've got a weighting function. But the interesting part is this D function, which essentially measures the distance between it measures the distance between two qubits when they're put on the circuit. And that more or less measures the number of interactions. So what it says is, those with fewer interactions lead to good low cost, and we should be placing those in certain qubits. Now, we said we can't try all the placements. So how many do we need for a given circuit on a given processor? And the simple answer is that we don't know. These heuristics are usually based on things like genetic algorithms, and you more or less set a number of generations and you leave it to run. But no one knows before the outset just how many placements you need to try for a given circuit on a given processor, and that's a bit of a problem. Swap insertion actually works largely the same, because you can think about swap insertion. Swap insertion works on like a step-by-step basis. You can think of swap insertion as rearranging the initial placement for the remainder of the circuit. And these metrics, the D metrics, the distance between, they are evaluated over the entire length of the circuit. But the question is, do you need the entire length of the circuit? Because clearly the more of the circuit you evaluate, the more complex your algorithms are, and the longer they're going to take. It probably shouldn't surprise you very much that I tell you that no, you don't need the entire circuit. But the question is, how much of the circuit counts? How much should you be looking at? No one, again, can answer that question right now. It's all a bit airy-fairy and hand-wavy, and there are techniques out there, but no concrete measures on how to use the techniques to reduce complexity. So I just want to give two examples of how sort of very simple classical thinking around these two problems can produce pretty dramatic results. So the first one's placement. So we did a little experiment which essentially took 20 random qubit circuits. There were 4 qubit circuits. There were 250 gates long each, and we did exhaustive mapping of all the circuits onto a 2x4 grid. And for each of those, we did swap insertion, and we come up with the final swap cost. And there were a lot of options, as I'm sure you can see. But the distribution of swap costs looks like this, right? And it looks very much like a normal distribution. So the point is that the outcome of your entire process is normally distributed. And so we'll never be able to guarantee that we get the optimum solution using any heuristic. But as a designer, what we might want to say is, well, I'll take something that is, say, within 10% of the optimum. If I knew that my result was within 10% of the optimum, say 20% of, or sorry, 80% of the time, then I could live with that if I knew that I was getting a solution much more quickly. And you can do something about that. Once you know that the swap costs are normally distributed, you can figure out how many placement, a sample of placements, how many placements you need to perform in order to get to the bottom end of this distribution with a certain confidence. I mean, it's very simple statistics and based on cumulative distribution functions. So if we postulated that for any circuit, on any grid, we would get this sort of normal distribution, could we estimate how many samples we would need to take? In order to do that, we would need to know the statistics of the distribution for a given circuit on a given processor. And the mean statistics in a normal distribution are the mean, so the middle, and the standard deviation of the distribution. So what we wanted to know was, well, for a given processor, can we figure out the mean and the standard distribution, or at least try to estimate it, so that then we would know precisely how many placements to try in order to get and ultimately get a solution which is within a certain percentage of the optimal, a certain percentage of the time. The simple answer to that is absolutely yes, that you can. So we did this for a number of qubits, and we did it for a number of grid shapes. So the straight on the left-hand side here, this is how the mean varies. So for 3 to 8 qubits, you can see it's a nice line for linear, and it's a nice line, a nice straight line for the rectangular formation. The reason why you get a difference for linear and rectangular is because there's a relation between the mean of these distributions and the distribution of the distances between 2 qubits on the chip, which changes as the dimensions of the chip changes. So you can, and it's a nice straight line when you're trying to estimate the mean. You can do the same with standard deviation, as the right-hand side shows. So now that I know the mean and the standard deviation, and I know that the trend is a straight line, I could potentially say, well, for a 16-qubit grid, what's the mean? What's this? If it's a 16-qubit grid and it's rectangular with a certain largest dimension, I can therefore estimate the mean and the standard deviation, which will then allow me to figure out how many placements. And if I do that exactly that many placements, and I apply swap insertion to each, will I get to a solution which is as good in terms of the number of swaps much more quickly than I currently can? So it would be a tremendous anticlimax if I said no, and in fact you can. So we did this for a benchmark set, which is probably about 20 circuits. And the column you should be looking at here is the one on the right-hand side, which shows the decrease or increase in terms of the number of swaps, and the decrease or increase in the terms of the number of the runtime. So in this case, positive is good and negative is bad. But for instance, you can see that, I mean, for 6 at the top rows, you can kind of ignore anything. 6 qubits is kind of, even doing an exhaustive search, you could do it quite quickly. So it doesn't really matter. The benefit is really at the bottom end of this table. But for instance, to pick out some numbers, a 10-point quantum Fourier transform, we can reduce the runtime by almost 98%. There's a degradation in the number of swaps that we get when we do that in that particular circuit by about 16%, so about 1 in 10. But in others, let's say once we get to 15 qubits, this is the ham15_108 circuit. Is a 15-qubit circuit. We get there 98.4%, and the result is actually 10% better. And in fact, the 10% and the 16%, those are sort of the heuristics that we're using they're non-deterministic and statistical anyway. So you get that variation naturally between runs of the system. But on average, we're looking at increasing speed by about 84%, reducing the amount of time by about 84%. For really only an average increase of about 0.16% in terms of the number of qubits. So that's a good deal, right? And that really didn't involve me or my student who did this work knowing too much about entanglement or trapped ions or whatever else, right? This is standard classical stuff. Okay, so for swap insertion, the question then is the metrics are evaluated on the entirety of the circuit. And the question is, does the entirety of the circuit matter? And again, the answer is no. We created a number of random placements, and we looked at not the total number of swaps, but how the distribution of swaps changed across the circuit. And you can see the results on this chart. So the green line was the best swaps per gate. So we use swap density to essentially say the number of swaps for every 10 gates. And you can see that it starts really, really, really low and then increases to something like 0.4 on average, which essentially means you're putting in a swap every other gate. The worst solution starts at 0.7, but interestingly then it improves as things go on to almost the same point. And in fact, if the gate depth increased further, you would find that these would get closer and closer and closer together asymptotically. So the point we're trying to make here is that it doesn't really matter if you start within you start with a really bad placement or a really good placement. What matters is that within a certain number of gates, you're only a percentage difference apart anyway, and it may be that you could accept that tolerance in the quality just to get there more quickly, right? And so we can use these gate depths to define the depth of circuit, how much of the circuit we look at when we're evaluating the metrics for swap insertion. So the question we were asking is, how long a window do we need to get within a threshold of the best? We can estimate the window size from the swap density. This is much more of an empirical process. So essentially we start with a lot of random circuits, and for each one, we generate a number of placements using, by the way, the sampling that we looked at in the earlier. From each of those, we create our nearest neighbor compliant circuits using a standard swap insertion heuristic. From those, we average overall placements of all circuits, and we do the thresholding, which is the cutoff to say, well, we're within 10% within so many gates. We just scan along the swap density metrics and figure out when we get within 10% of the best that we observed. And you can do that for different thresholds. You can do it for 10%, 7.5, 5, or even far closer to the start. And the idea is that, for instance, when someone created a quantum processor, they could do this profiling before they release it, and this information could be built into the transpiler software to do the swap insertion more quickly. So we did it for a bunch of grid sizes, so 5, 6, 7, and 8. Well, actually, we did a lot more than this, but these are just some examples to show that, you know, even at 8 qubits, you can have thresholds of 34 gates for 10%, within 10% of the best, 39 within 7.5%, 123 once you get in 2.5%, if you want to get within 2.5% of the best. So you can tune the time and the quality of the results. So we applied this on the back of our sampling approach. So we did an estimated window size plus the sampling, and you can see that even relative to the runtime of the sampled placement approach, we're getting good reductions again. So even another 40-odd% on top of that for a 3x3 grid up to 4x4. Again, it's about 20%. And swap reduction, the swap cost, it goes up and down kind of as you would expect. Just to compare that with a fixed window size, you could just say, well, we'll not bother with all this profiling. We'll just stop at 10 gates. With no sampling, you get similar reductions, but the point here is that you constantly get increasing swap cost, and the increases are going up as the grids get larger. Okay, so there is benefit in terms of controlling or bounding the swap cost increase from doing this kind of pre-profiling. So that, I don't know how much time I've taken up, but that really is all I wanted to say. I guess the message I wanted to get across is that this is an extremely exciting and hot area. It's incredibly interesting. It appears on first inspection, if you want to get involved, that there is a very large barrier to entry. But I think the message that I want to get across here is that there isn't, right? Don't believe the hype. Whether or not large-scale quantum computing comes to pass, there's a lot of very useful crossover work that can be done right now. In hybrid classical quantum computation, it's the medium-term future, and a lot of expertise built up in the computer engineering community isn't it's not being used in the quantum computer engineering domain, but certainly the expertise in the room and on the call and the people listening to this is certainly relevant to solving a lot of very large problems. And I would encourage everyone, if you're interested, just to go in feet first. And so that's all. Thank you very much, everyone, for listening, and I'm happy to take any questions. Although if you ask me too much technical stuff, I may not know the answer.
Okay, thank you, John. Well, we're running out of time, but we have time for a few questions. We have a question in the audience.
Hello. Actually, it is very interesting that I got to know that. I actually work with mapping, so it is kind of like the whole scenario of quantum computers. It means like the placements was more of a mesh, and the placements we use particle swamp optimization or genetic algorithm, and we do this swapping, and also we do this nearest neighbors. So in this prospect, the shapes that you have taken is square and rectangle, means a rectangle and a triangle. So is it this rectangle is means like you are taking in a rhombus pattern, or it is just like a rectangle, a square in which you are connecting the points that they are in? Or are you shifting the window? Means the window can be rotated, or the window is fixed?
So it's certainly it's the second one. So we work with ideal. I mean, hands up, we work with ideal grids just at the moment. So they're square grids where we connect all the points, or rectangular grids. In fact, what you just referred to at the end there, the rotations, those are actually, there is a way to exploit that for very significant reduction in the number of points that you need to analyze whenever you're mapping to quantum processors. If you look at the structure of, the quantum processors that are out there, so the principles that I've been putting forth here are actually not based on the grid size. They're observations of, if we happen to use these grids, what would happen. The phenomena that give rise to the benefits we've seen are to do with sort of geometric measurements of distance inside the grids. Okay, and honestly, it doesn't matter what shape your grid is. The Manhattan distance between 2 points on average is still going to be calculable. But hands up, we've been looking at ideal grids at the moment, but the very next step is to look at, there are some very weird shaped quantum processors out there. The Google processors are probably the most regular, right? But there are certainly others out there which are not that regular. And we haven't looked at those explicitly just yet, but that's next on our list of to-dos.
All right, thank you.
Thank you, John. Maybe another question in the audience?
I have a question.
Okay, please.
Hi, John. I was wondering, you were speaking about hybrid systems, quantum and non-quantum and classical systems. Are some are people already putting up systems like this today, or is it like a horizon? And how do inputs, outputs, how do IOs between this system work? It's something I didn't get.
Are people developing those today? Yes, I think that they are. I'll not name names, but certainly there are some pretty significant multinationals that are looking fairly directly at this. Yeah, I mean the simple situation at the moment. I mean, whether or not they are, I think that conceptually it makes sense, right? Because if I've got quantum processors that have 20 qubits, but I know that the confidence that I know that I can only run a certain number of qubits with a certain confidence, then for any significant workload, you're going to have to do some of it in the classical domain anyway. So yes, there are people looking at that. There isn't a lot of work on things like runtime migration or that type of thing at the moment that you would find in normal classical systems. But I could certainly see it happening, and there are people looking at static synthesis of operators for either classical machines or quantum machines. And there are sort of emerging pieces of work that are looking at stitching the two parts together. And so I think that given the interplay between quantum and classical algorithms, I certainly think that that's very viable, right? If you're developing algorithms in the quantum domain, which are then leading to huge reductions in the complexity of classical algorithms, then you want to be able to move back and forth. In terms of practicalities on I/O, so I'm gonna have to say, hands up, I don't know, and that's largely because most of the companies who are developing these are extremely tight-lipped on their hardware. They seem to be quite open on their software, but not their hardware. But I would imagine it's going to be quite slow serial links into a cryogenic fridge and back out, and that's a big ask.
Okay, thank you.
Okay, thank you, John. So I think we can move to the next talk and thank John again.
Thank you.